Let's now look at the last example where I have the cubed root of 250 x to the 7th y to the 20th. Now I have a numerical coefficient of 250 inside the radical, so I want to take that down to its prime factors and to see if anything out of that can come out of the radical in its simplified form. And with the variables, I could write them out without their exponents, but it would be a lot of writing and it would be a very long expression to simplify. An alternate way would be to look at how you could break apart the factors of x to the 7th, where you have them in groupings of factors of x, that the exponent is divisible by the index, and then whatever the leftover is. And that's the way we're going to handle it in this particular example. So let's first start with writing our cube root and taking the 250 and finding 250's prime factorization. Well, 250 is divisible by 2. It's 2 times 125. 2's prime. 125 is divisible by 5. It's 5 times 25, and 5's prime. And 25 is 5 times 5. 5's prime and 5's prime. So here I have my prime factorization of 250 is 2 times 5 times 5 times 5. And notice these are individual numerical factors. For the x's, instead of writing x times x times x times x times x times x times x, 7 factors of x, which would make it really long, what I'm going to realize that every 3 groupings of my factors of x would be something that could bring an x out. And the exponent is what shows me that I have that many factors of my base of x. So I want to think with the exponent I have on my x, what number lower than my current exponent under the radical, but as close as I can get to it, is evenly divisible by the index. Well, since my index is 3, I want numbers that are divisible by 3. And the number that's just below 7 that's divisible by 3 is the number 6. So I'm going to have x to the 6th, and then I would need an extra factor of x to still mean the same thing as x to the 7th under the radical. For y's exponent 20 is not currently divisible by 3. The number that's divisible by 3 that's still less than 20 but really close to it is 18. So I'll write it as y to the 18th, and then I still need a y squared to overall still be the same thing as the y to the 20. Now let's go ahead and bring out what can come out of the radical. When I have my cube root, the 2, there's only one factor of 2, so it has to stay under the cube root. But I have 3 factors of 5, and under a cube root, that's enough for a 5 to come out. Next up, the x to the 6th. When you have a base to an exponent and you're finding the simplification of that out of a radical, you keep the base and take the exponent that's under the radical and divide it by the index to get the exponent that should be on your base outside the radical. So I keep my base of x, and 6 divided by 3 is an exponent of 2. And this ties back to the fact that radicals can be written as fractional exponents, and the denominator of the fractional exponent is the index. So we're basically just simplifying those fractional exponents. Okay, so that took care of the x to the 6th. I have this factor of x that's exponent is 1, and an exponent of 1 is smaller than my index of 3, so that has to stay under the radical. Next, the y to the 18th. I keep my base of y, I take my exponent of 18 and divide by my index of 3, and that gives me an exponent outside the radical of 6. And then my last factor, y to the 2nd, 2 as an exponent on my base of y is an exponent that's smaller than the index, so that can't come up. So y to the 2nd. So this is the simplified form of our original radical.